Hereby, I open this academic ceremony in which Rodrigo Fabian Mancilla Fuentes will defend the academic thesis, Novel Aspects of Exercise Training to Promote Human Metabolic Health. May I invite you to present a summary of your study and the conclusions of your thesis.
Dear Prorector, members of the Corona, family, friends, and the many of you who are following online. Welcome to my defense. In the next 15 minutes, I will introduce you to my dissertation entitled Novel Aspects of Exercise Training to Promote Human Metabolic Health. Worldwide, the prevalence of obesity has drastically increased in the past 10 years, reaching proportions of at least 20% of the population. In essence, obesity is expressed as an excessive fat accumulation in the adipose tissue. In addition, fat accumulates in other tissues, such as skeletal muscle and liver, negatively affecting metabolic health. For instance, causing insulin resistance, a condition that is part of the type 2 diabetes disorder. In normal conditions, plasma glucose levels rises upon feeding. In response, plasma insulin levels elevate to maintain normal glucose levels. To do so, insulin targets specific cells of our body and initiate a signal to incorporate glucose into the cells. Once inside the cells, glucose can be burned to produce energy or can be stored as a bank of energy. In the context of insulin resistance, there is a disruption of the signal induced by insulin that results in less glucose uptake, less energy production, and less energy storage. In response, more insulin is produced to normalize plasma glucose levels, the energy production, and energy storage. There are multiple pharmacological products aiming to control plasma glucose levels. However, regular exercise training and diet are the most powerful strategies to prevent and improve insulin resistance. Regular exercise training is well known to improve whole body insulin sensitivity. In addition, exercise training decreases fat accumulation in the liver and increases skeletal muscle mitochondrial function, which together improve metabolic health in obese insulin-resistant individuals. These benefits provide the basis to recommend exercise training as the first-line strategy to prevent and to treat insulin resistance and type 2 diabetes. The current exercise recommendations to prevent and to treat insulin resistance is to perform aerobic type exercise, strength type exercise, or the combination of the two, at least 3 times per week, aiming to accumulate 150 minutes of activity in total. Although these type of exercise modalities have shown positive effects to improve insulin sensitivity, the magnitude of the benefits is not equal across subjects. In fact, there are individuals who actually decrease insulin sensitivity or simply do not change after following these exercise recommendations. Other important factor is that obese insulin-resistant individuals exhibit a poor exercise tolerance, negatively affecting the results of these exercise modalities. Therefore, it is important to come up with novel strategies to optimize the benefits of exercise training on insulin sensitivity and to improve insulin resistance and the exercise intolerance in these subjects. In this context, the objectives of this thesis were to investigate novel strategies of exercise training to optimize the benefits on insulin sensitivity and to identify potential targets of intervention to improve exercise intolerance. For these objectives, 3 studies were conducted in humans. The first study to test the effects of exercise timing by comparing morning versus afternoon exercise. The second study to test the effect of high-intensity interval training. And the last study to investigate muscle metabolism at the onset of exercise. Multiple studies have shown that human metabolism exhibits circadian variations over the day. For instance, insulin sensitivity peaks in the morning. Physical performance and mitochondrial function peak in the afternoon, while body temperature is lower in the morning. These discoveries raise the question if there is a more optimal time of the day to exercise to amplify the benefits of metabolic health. To answer this question, 3 groups of subjects were investigated. The first group was classified as obese. The second group had non-alcoholic fatty liver disease. And the third group was classified as a type 2 diabetes patients. The participants performed aerobic type exercise using a stationary bike, combined with a strength type exercise under supervision. The participants performed all the training sessions, either in the morning or in the afternoon, 3 times per week during 12 weeks. The parameters that we measured were insulin sensitivity by the clamp test, body composition by the BOD-POD technique, and the maximal exercise capacity through a cycling test. The results. In terms of insulin sensitivity, we found that the group of subjects who trained in the afternoon, as shown in the blue bar, improved to a greater extent as compared to the group of subjects who trained in the morning, as shown in the yellow bar. In terms of body fat content, we observed a greater decrease in the group who trained in the afternoon as compared to the group who trained in the morning. As last, exercise capacity improved more in the group who trained in the afternoon as compared to the group who trained in the morning. Our results suggest that exercise training induces superior metabolic effects when performed in the afternoon as compared to morning in metabolically compromised individuals. The effects of exercise on insulin sensitivity have been shown to be dependent on the intensity of exercise. In fact, high-intensity exercise leads to greater improvements on insulin sensitivity. Therefore, it seems appropriate to recommend to obese insulin-resistant individuals to perform exercise at high intensity to get greater insulin sensitizing benefits. However, intense efforts cannot be sustained for long duration. In consequence, high-intensity interval training, known as HIIT, is a feasible option, as this includes short bout of exercise performed at high intensity, followed by short periods of resting or partial recovery in between. To investigate the effect of HIIT, obese adults, males and females, participated in our study. The participants performed a HIIT training program using a stationary bike, which consisted of 10 bouts of 1 minute cycling, followed by 2 minutes of resting in between each bout. The intensity of the cycling was between 80 to 90% of the maximal capacity of the subjects, and this was performed 3 times per week during 12 weeks. The participants were divided into 2 groups. One group who consumed water after each training session, and the other group who consumed glucose and proteins after each training session. This is relevant given that the consumption of glucose and proteins after exercise has become a common practice nowadays. The parameters that we measured were insulin sensitivity by the clamp test, liver fat content, and skeletal muscle oxidative capacity by magnetic resonance spectroscopy technology, and the maximal exercise capacity through a cycling test. The results. In terms of insulin sensitivity, HIIT significantly improved insulin sensitivity at the same level in both groups. In the one who consumed water after training, as shown in the white bar, and in the group who consumed glucose and proteins after training, as shown in the orange bar. In terms of exercise capacity, HIIT significantly improved the maximal exercise capacity at the same level in both groups. When looking at liver fat content, HIIT tended to decrease liver fat content at the same level in both groups. In terms of skeletal muscle oxidative capacity, HIIT significantly improved skeletal muscle oxidative capacity at the same level in both groups. Our results show that high-intensity interval training is an effective training method to improve metabolic health in obese adults, regardless of the consumption of glucose and proteins after training. Trying to understand exercise intolerance in humans, we investigated muscle metabolism and energy production at the onset of exercise. In fact, when exercise starts, there is an exponential increase in the energy need by skeletal muscle. This energy need is primarily buffered by the energy stored in muscle in the form of phosphocreatine, or PCR. The reliance on PCR occurs until muscle mitochondria is activated. In case of a delayed activation of muscle mitochondria, there is a large utilization of PCR, negatively affecting muscle contraction. In this context, it is expected that a slow activation of muscle mitochondria at the onset of exercise contributes to exercise intolerance in humans. Therefore, by looking at the dynamic response of PCR in muscle at the onset of exercise, it is possible to investigate the speed of activation of muscle mitochondria. To investigate the dynamic response of PCR in muscle at the onset of exercise, we set a non-invasive method by using magnetic resonance spectroscopy technology. Here, subjects can perform one-leg knee extension and flexion exercise inside the scanner. With this method, we can quantify the utilization of PCR at the onset of exercise, known as PCR on kinetics, until reaching a new steady state when mitochondria is activated. By this method, a short PCR on kinetics reflects a fast activation of muscle mitochondria at the onset of exercise, while a long PCR on kinetics reflects a slow activation of muscle mitochondria at the onset of exercise. To investigate if the speed of activation of muscle mitochondria at the onset of exercise is different between metabolically compromised and healthy individuals, we apply our methodology in a group of subjects composed by endurance-trained, lean-on-trained, obese, and type 2 diabetes patients. In addition, we apply our methodology in a second group of subjects composed by young, healthy, and older individuals, classified as a trained and with normal physical activity. The results. We observe from group 1 that the speed of activation of muscle mitochondria at the onset of exercise is drastically slower in obese and type 2 diabetes patients as compared to healthy individuals. When looking at group 2, we observe that the speed of activation of muscle mitochondria at the onset of exercise is similar between young, healthy, and older trained individuals, but drastically slower in older with normal physical activity. Finally, we investigated if the speed of activation of muscle mitochondria at the onset of exercise is associated with physical function. For instance, with the transitions of sitting and standing from a chair and walking speed. We observed that an impaired capacity of sitting and standing from a chair is associated with a slow activation of muscle mitochondria at the onset of exercise. In addition, we observed that a slow walking speed is associated with a slow activation of muscle mitochondria at the onset of exercise. From this thesis, it is possible to conclude that timing of the exercise is an important factor when aiming to improve glucose homeostasis. That performing exercise in the afternoon is more optimal than morning in metabolically compromised individuals. That high-intensity interval training is an effective training method to improve glucose homeostasis and metabolic health in obese adults. That there is a delayed activation of muscle mitochondria at the onset of exercise in metabolically compromised and older individuals, linked to impaired physical function, which can be rescued by regular exercise training. With this, I would like to thank you for your attention and give the word back to the prorector.
Thank you for your presentation. The opposition will be opened by Professor de Galan, Professor of Medicine and Diabetology at this university. Professor de Galan was chair of the assessment committee and is the secretary of the degree committee.
Thank you very much, dear candidate. First of all, I'd like to congratulate you with achieving this milestone of completing the thesis. And for that, I also like to extend my congratulations to your supervisor and team. I enjoyed reading your thesis very much, and I think it's also very topical in this era, since what we know about the relation between poor metabolic health and COVID-19. And it emphasized the need for good exercise to become physically fit and stay fit as well. And on the other hand, the many lockdown measures that we've experienced make that a real challenge. And that brings me already to my first question. As you know, during the last COVID wave, the Dutch government closed fitness centers and outdoor sporting fields between 5 p.m. and 5 a.m. the next morning. Now, with your experience or your opinion, your knowledge that you wrote in your thesis, what is your opinion about what the government should have done in terms of closing the fitness centers? Would that be as it is now, or from your perspective, would you do something different?
They're highly esteemed opponent. Thank you very much for your kind words and also for your question. If I understood correctly, the question is about what I think about the current situation regarding the gym facilities, isn't it?
Yeah, so the government closed the fitness centers and sporting fields between 5 p.m. and 5 a.m. So it's open during the day. Now, from your perspective, would that be a wise thing to do, or would you do otherwise?
Well, my primary advice is to keep moving. We need to exercise for sure to keep up our health. Doesn't really matter still if we do it in the morning or we do it in the afternoon. Nevertheless, time matters if we want to optimize the benefits. In that regard, we found that timing of the exercise might influence the benefits of exercise on insulin sensitivity. We found that timing of the exercise might influence the performance. But in that context, I understand that the people nowadays doesn't really care that much about performance. What is most important for them is to keep, for example, metabolic health in regards of insulin sensitivity or decrease the fat content in the liver, in the body. So my advice could be, at this time, exercise whatever time you can. If you can and want to optimize your benefits, you can do it in the afternoon. But if you can do it in the morning, you can also do it. And if you don't have the facilities to exercise indoor, you can still do it outdoor, whatever time you can.
Okay. So it doesn't matter yours. I mean, if I look at your chapter 3, for example, and also in your presentation, say training in the afternoon is much better if you look at the necessity or whole body glucose disposal when compared to doing it in the morning, right? Mm-hmm. So that is what your conclusion in chapter 3. But if I look in your description, you say on page 47 that the analysis on glucose disposal and oxidation was based on a smaller number of participants because of some technical issues. And when I look at the original paper that was published many years before, when there was no discrimination between morning or afternoon exercise, in that paper it was said that the effects on insulin sensitivity was much more pronounced in people with type 2 diabetes compared to people without diabetes. So my question is whether the number of people that you use in this analysis were those mainly people with type 2 diabetes, and could that have explained the difference between the morning and afternoon effects that you found?
Yeah, so in fact, we only include a small amount of subjects in both groups who actually exercise in the morning or in the afternoon, who were classified as a type 2 diabetes people. So I am aware of the paper that you mentioned on which they say that people with type 2 diabetes will for sure perceive and also obtain more benefits as compared to healthy people exercising at whatever time. But I think we are starting to understand the connection between the exercise metabolism and, for example, the circadian biology. In that regard, I would say that, for example, to really grab the effects of exercise, as I said before, doesn't really matter at the time. In our paper, we cannot conclude specifically if type 2 diabetic people will obtain more benefits exercise in the afternoon, as we collected data from people with non-alcoholic fatty liver disease and also obese. But current literature also announced that people classified as a type 2 diabetic people, as a type 2 diabetes patients, they will perceive more benefits in terms of glycemic control in 24 hours. That has been shown, for example, by the group of Professor Julien Seriat, who showed that after 2 weeks of high intensity interval training, people with type 2 diabetes will grab more benefits when exercising in the afternoon, while exercising in the morning, they still perceive deleterious effects in the glycemic values.
So when I can follow up on that, if you look, so you say, I mean, exercise in the morning and afternoon, I mean, it's both good, right? Mm-hmm. It may be a little bit better in the afternoon than in the morning, but it's both good. But if I look at your study in chapter 3, and I look at the effects you describe or you show in the figures in the table, I actually don't see any effects of morning exercise.
So I cannot really hear you very well, sorry.
So if you look at the figures
Yeah.
on page 48 and 49 in the table 2, and you look only at the effects of morning exercise on the morning sessions, the training, the 12 weeks training in the morning, I don't see any effects on insulin sensitivity in terms of glucose disposal, glucose oxidation. And in fact, I see that fasting glucose even increases, it tends to increase. It's not significant, but it tends to increase. I would expect it to reverse. So would you conclude from that that morning exercise doesn't have any effect?
No. In fact, exercise in the morning also provides some benefits to insulin sensitivity. In this regard, we need to be aware that it's data collection with 3 different categories. We didn't have the power to really classify, not to classify, but to show what would be the different response in these 3 groups. But I understand that in the morning exercise has shown, as I say, deleterious effect on which, for example, acutely exercise in the morning seems to promote a higher endogenous glucose production relative to the glucose uptake in the muscle. Therefore, it might promote hyperglycemia. But in the long term, here we were able to show that indeed, if comparing morning versus afternoon exercise, afternoon is more optimal. But we didn't explore the effect of training.
No, but what is then your explanation for your increase in fasting glucose in the morning with the morning exercise? I mean,
yeah, that is something that we and also others don't know. But as I say, in the old literature, especially coming from Denmark, Professor Flemming Della showed that exercises in the morning, especially in the fasting conditions, promote a higher endogenous glucose production relative to the glucose disposal in muscle, which ended up being in hyperglycemic events.
Can I come up with an alternative explanation? So you say that diet didn't have an effect, right? So you say the diet didn't change.
The diet didn't change.
Right. Based on what?
Yeah, so we also need to be aware that this is a retrospective analysis. What I understood is that dietary records were provided from the participants on which they informed that the diet didn't change during the 3 months of intervention. But that was only not in detail explored, not in detail examined, only by, how do you call it, advices of not changing the diet throughout the intervention period. So would be really interesting to really see whether diet by people changed during the exercise training intervention, but in this case, we couldn't
I think, I mean, this is just my personal experience, but many people who do exercise feel good about it and then treat themselves, do something sweet, for example. If you do exercise in the morning, you have more time during the day to treat yourselves than if you do it in the afternoon. Could that be an explanation?
Do you mean that people consume more, for example, glucose in this case after exercising in the morning? It might be, but still the effects of the acute exercise session will remain during the 24, 48 hours on which the hyperglycemic peaks will be blunted. So I assume that the glucose stay activated to promote glucose uptake during 48 hours at least. But if we see this in a long term, the training adaptation will kick in, and therefore people will become more insulin sensitive.
Right. Okay. Do we have time for another short question? Let's move to chapter 6. There you investigate the effect of HIIT training. Really nice study, I must say. But I was a bit surprised that you allowed people to choose between the morning and the afternoon exercise. I thought with your knowledge that you described in chapter 3, you would stick to the afternoon exercise to optimize the effects. So what did you, why didn't you choose for that? And if you didn't, did you compare the morning and the afternoon exercise in this respect? Look at the outcome of insulin sensitivity.
Yeah, so in that particular study, our primary goal was to investigate the effect of HIIT in the non-oxidative glucose disposal pathway. As a secondary analysis, we of course aim to investigate whether HIIT improves insulin sensitivity as expressed by the glucose disposal rate upon insulin effects. This particular aim we didn't explore explicitly, but by not practical reasons, but as explorative objective, I would say, we delivered the opportunity to participants to pick the time that they select as a best for them to train during the day. I can say that mostly of the people who pick one time since the first exercise session remain until the 3 months of intervention. So we are now in the phase of analyzing the data, most likely as a secondary analysis. Sorry, supervisor, but we might do it, although we haven't discussed it yet. But it's something that we might get at some point.
I look forward to that publication, and thank you for your
Thanks very much.
the work back to Mr. Professor. Thank you.
The opposition will be continued by Professor Moyo, Professor in Medicine and Endocrinology at the Duke University in North Carolina, US. Professor Moyo was also member of the assessment committee, and we highly appreciate your contribution to this academic ceremony.
Mr. Candidate, I too would like to congratulate you on your accomplishments. I very much enjoyed reading your full thesis. I think very interesting results and really quite relevant to to a lot of clinical settings and I would say clinical problems that we're confronting right now. Two areas of questioning, one in chapter 3 and then chapter 4. So just to follow up on the questions that you were just discussing, in chapter 3, the results of the training study at different times of day were very reminiscent to me of some work done in rodents looking at the adaptations to time-restricted feeding. And in those models, also you see that the animals adapt so that they can much better defend their blood glucose levels throughout the day. So there's much less fluctuation in glucose. And I think, at least in part, that's mediated by adaptations in the liver. So I'd like you to elaborate on what you think the role of the liver is in mediating, the observations and the differences between the time of day, and then think maybe a little bit more about, is this necessarily a bad thing, a good thing? What, from an evolutionary perspective, why did the biology evolve? I'm sure the mechanisms are quite complex, but why would the organisms evolve in that manner?
They are highly esteemed opponents. Thank you very much for your question and also for your words. Indeed, there is a phrase going around like, tell me how long is your fasting and feeding condition or time window is, and I will tell you how healthy you are. In that regard, the animal models that you announced, better said, indeed, they show that under time-restricted feeding conditions, the animal seems to better respond to glucose challenges over the day. In that regard, the liver plays a central role. It is well known that the liver is one of the main disposal sites where glucose takes place, where the glucose disposal takes place. In that context, when the period without food ingestion, mice and humans need to keep up the glucose levels in plasma, on which the glucose, the liver is the main precursor of the glucose levels in plasma. So I think the liver plays a central role in that regard. Nevertheless, it's also important to remind that prolonged fasting conditions also might provoke deleterious effects in the liver by ectopic fat accumulation if the lipolysis is up and running. But I think the liver is central in regards of maintaining euglycemia, and that might be even better trained in conditions where the fasting and feeding time window is more prolonged. From an evolutionary point of view, in conditions, for example, where humans were not exposed to constant feeding conditions as we are nowadays, the liver indeed play a central role as maintaining euglycemia in blood. But at the same time, it's important to keep in mind that that the liver might become insulin resistant in conditions where it is exposed to elevated free fatty acid conditions. Therefore, the liver might also try to reserve their own glucose as a glycogen to maintain euglycemia in conditions where it is needed. So it's a balance between the energy stored in the liver with the plasma, with the glucose concentrations in plasma. I think the liver is also a plastic organ, like the muscle is. So I understand that the liver can also adapt to different conditions and stimulus.
Okay, thank you. Let's move to chapter 4. And it was a very nice study that focused on this concept of metabolic inertia. And in your work, so I had the impression that the enzyme CRAT is a major focal point. You propose that the interconversion of acetyl-carnitine and acetyl-CoA might be critical for maintaining energetics during the transition from rest to high levels of exercise. And so I'm wondering if you could you comment on, do you anticipate that the muscle pool of acetyl-carnitine is sufficient to maintain the acetyl-CoA pool for any length of time? Do you think that this I guess the phenomenon of metabolic inertia is largely or entirely connected to acetyl-CoA and CRAT?
Based on animal studies, indeed, it has been shown that CRAT protein activity modulates this conversion of acetyl-CoA from acetyl-carnitine, the acetyl-carnitine pool in muscle. But at the same time, this acetyl-carnitine pool in muscle might come from other tissues that indeed release, for example, acetyl-CoA connected with carnitine. So these molecules can transfer the membrane and therefore might come from other tissues as well. In that regard, the acetyl-carnitine pool that we observe in muscle, we made the connection with the initial phase of exercise, given that, as I say, there is a certain deficit of acetyl-CoA at the starting of the exercise that might imply a delay activation of mitochondrial function, or mitochondrial ATP generation. If that happens, PCR will deplete and therefore muscle fatigue will come pretty soon, interfering with performance at the end. During the exercise phase, animal data again have shown that acetyl-carnitine might provide acetyl-CoA groups for mitochondrial oxidation that has been shown in animal models and also in cell models exposed to electrical stimulation, and observed by tracking the carbons from the acetyl-carnitine molecule that this acetyl-CoA coming from acetyl-carnitine goes into mitochondria for oxidation and ATP generation, and even promoting performance. But that has been shown in animals, not in humans yet.
Okay, yes, and so just to follow up on that, the circulating concentrations of acetyl-carnitine are in the low micromolar range. And so again, I question whether that low concentration on its own, I believe you that CRAT plays a role in all of this, but I'm wondering if there might be other components, because that acetyl-carnitine concentration is quite low. And the studies that you referenced where the muscles were contracted and acetyl-carnitine had a benefit, one of the caveats of those experiments is that much higher concentrations of acetyl-carnitine were used in the experiment. So again, I'm just challenging you to think about, do you think that CRAT and the acetyl-carnitine conversion is the entire story, or could you imagine other mechanisms that cooperate with CRAT to mediate this effect, and what might they be?
Indeed, I think that there are other parallel mechanisms that also contribute to the acetyl-CoA influx into mitochondria. For example, mediated by PDH flux that has been shown by Professor Paul Greenhalgh from Nottingham University back in 2002. He showed nicely that indeed by stimulating PDH by the use of pharmacological products like dichloroacetate, even in epoxy conditions, there is an accumulation of acetyl-CoA in the form of acetyl-carnitine, which at the end will be provided to the mitochondria for oxidation. So I think there are parallel mechanisms to that. Next to that, we also assess, for example, the ADP concentrations in muscle during exercise, especially in the phase of the initial contraction until PCR reaches a new steady state. What we try to bring there is that next to CRAT, it might be an intrinsic capacity of the mitochondria to sense the energy stress on energy demands. If the mitochondria is healthy enough, might sense properly the ATP concentration to promote the ATP formation through OXPHOS. So it might be different mechanisms that contribute to the ATP generation by oxidative phosphorylation and therefore to sustain muscle contraction.
Okay, thank you for your answer. I don't want to go over my time allotted, so I will move over to the next opponent.
Thank you. The opposition will be continued by Dr. Khan. Dr. Khan was member of the assessment committee and she is radiologist at the Leiden University Medical Center. Also, thank you for your participation to this ceremony.
Thank you, Mr. Prorector, and thank you for inviting me to this ceremony. And Mr. Candidate, first of all, I would like to congratulate you and also your supervisors, of course, with this work, because for me, this thesis really presents a very nice overview of a very multifactorial and timely topic. And I was really impressed that you showed that you mastered different aspects of this problem by presenting data obtained using a range of techniques. And you will probably not be surprised that I will mainly focus my questions on chapter 4, which deal with the MR spectroscopy part of the work. Because in this chapter, you introduce, at least for me, new methodological concept, which is called the PCR on kinetic, and it was already alluded to a little bit by the previous opponent, as a marker for mitochondrial inertia. And when looking at the literature, I saw that it was used before, but not much, and quite a long time ago. So I think that if more people would use this metric, it would provide a very important contribution to the field. However, I would like to challenge you a little bit on the way you obtained this metric. But first, I would like to start with a small technical question, because when reading up on the methods, I noticed that you took two approaches to the peak fitting in your MR spectroscopy data, where you used PCR fitting using MATLAB for the PCR on kinetics, but then later on, when you fitted the ADP, you used JMRI. So why would you use two different approaches?
Dear esteemed opponents, thank you very much for your question and also for your kind words. If I understand correctly, you are asking me why we decided to take a different approach to fit the lines of the PCR dynamics at the initial of exercise and at the end of exercise. In that particular case, at the end of exercise, it is assumed that the resynthesis of PCR occurs purely by oxidative phosphorylation. In that context, if we, for example, create an epoxy condition, basically there is no PCR resynthesis. So that is the assumption that it is purely oxidative. In the context of the initial phase of exercise, there might be a parallel contribution of other alternative energetic pathways, like for example, glycolysis. So the idea is that if PCR depletes until reaching a new steady state as quick as possible, is because mitochondria will kick in, and therefore there is an spare of the PCR pool and probably also of the glycogen pool. So these two dynamic response of PCR seems to reflect different processes occurring in the muscle, specifically at the level of mitochondria.
But then why would you use MATLAB to fit the PCR peak and use JMRI to fit ATP or ADP signals?
Technically, I cannot answer that question, but JMRI was used to distinguish whether there are left signal after applying some sophisticated, how do you call it, to investigate if there are residual signals from the PCR, or better say, let me think, is to properly distinguish if we can observe the 3 different ATP peaks at the resting condition to use as a reference.
Mm-hmm.
And at the end of exercise, the MATLAB script is utilized to purely fit the recovery of PCR. But I'm not sure why technically these two software are used. I'm not in the position to really provide you a good answer about that.
That's fine. So, but because you alluded to it a little bit when you answered my previous question, because that was another thing I was wondering about, because when you talk about the PCR onkinetic, you say that you assume that the PCR depletes, right? And that's the only source of energy. But when depleting PCR, you also consume protons, right? So there should be an effect on the pH as well. When oxidative phosphorylation is switched on, there's also an effect on the pH, but you did not show any dynamic pH data. You showed end of exercise pH and you showed, I think, end of recovery, but not pH dynamic. So have you looked at that, and do you think it would help you?
It might help, but indeed we use the pH values as at the start of exercise and at the end of the recovery phase, on which we observed that there was no changes in pH. pH might highly be influenced by the exercise intensity. As you say, pH might delay the recovery of PCR and might also delay the onkinetics in this case. The assumption of the equilibrium constant formula of the creatine kinase reaction indeed is that pH doesn't change. From practical experience, we know that by applying these exercise intensities between 50 to 60%, we will observe a depletion between 30 to 50% of the PCR pool. And that has been shown by years that we don't observe any pH changes. If that happens over time, I don't think so. Because if we measure this pH at the end of exercise, for sure will be also different if something happened in the time window of contraction.
Yeah, no, I think we agree on that one. Because you just mentioned, right, that you aim for a PCR depletion between 30 and 50%, which seems like quite a broad range. And looking at your figures, for instance, figure 2A on page 72, you also see quite a big difference between your subjects in PCR on kinetic. I know that you really focused your studies on looking at differences between groups, but also did you also look at where this difference within one group comes from and whether this could be due to exercise intensity, for instance?
If the exercise intensity, as I say, plays an important role in the PCR depletion. Whether this was different across the subjects, across the groups, we didn't explore in detail, but indeed I observed that, for example, type 2 diabetic people seem to have a higher depletion compared with the endurance subjects, with endurance trained subjects. But again, what we measured here was the dynamic response of PCR, given the fact that we didn't compute, for example, the absolute concentration of PCR. If we were able to compute the absolute concentration of PCR, we might talk about levels or percentage of depletion. As we standardize the exercise protocol to certain intensity to reach certain amount of depletion, we found more interesting to see what is going on with the dynamic response, with the kinetics of PCR until reaching this steady state, rather than only using absolute concentrations.
But they all reached a steady state, right? Because I think you mentioned in a method somewhere, we only looked into the subject where we could determine the steady state, but I could not find anything about quality control. Like, how did you determine whether they reached that steady state?
The reachment of the steady state was mainly done by, not by eyes, I would say, but we clearly observed that every single person who was included in that chapter reached clearly a steady state. So therefore, we fit the PCR on kinetics since the resting condition until the first point of the steady state.
But what do you mean by clearly?
Clearly that since the starting of the steady state, that steady state continue until the end of the exercise.
Okay, thank you. I think I've used up my time. I could continue, but
Okay, thank you.
Thank you.
The opposition will be continued by Professor Wojciechowski, Professor Muscle Metabolism, Physical Activity and Health at the University of Copenhagen in Denmark. Also highly appreciated your contribution to this academic ceremony. Professor Wojciechowski.
Thank you, Mr. Co-Rector. Dear Mr. Candidate, congratulations with a very nice thesis. And I would like to congratulate you as well as your supervisor for very sophisticated studies and very nice readouts. So that's, I'm really impressed. I also like to read your thesis. It was clear to me. I could follow your thoughts. So you should be applauding yourself, at least for now. So thank you for that. I think I will jump all the way down to chapter 6, where you study the effect of HIIT training. You use the clamp to measure insulin sensitivity. Could you just remind me what is the clamp? What type of analysis is the clamp?
They're highly esteemed opponents. Thank you very much for your kind words and also for your question. The time that the test lasts, or the time that the test was performed. Either way, the test was started at 7 a.m. The time duration of the two-step hyperglycemic hyperinsulinemic euglycemic clamp was around 8 hours, 8.5 hours in total.
Yeah.
With,
so with
3 hours. Sorry.
So with the clamp, I was just yeah. So you're measuring insulin sensitivity by the clamp technique, the gold standard.
Yes.
Yes. Yeah. So what concentration of glucose are you using during the clamp?
What type of glucose?
What is the concentration?
What concentration? The concentration is in millimole per body weight, at least of the tracer infusion. The amount of glucose that we infuse to sustain euglycemia, of course, differs per subject, but it's around, for example, in the pre-exercise condition, pre-training condition, I think subjects reached an infusion rate of 100 milliliters per body weight, and then increase it after the training phase.
Yeah. So but you said my question was, what was the concentration of glucose? And you say euglycemia, so it's around 5 millimolar. Yes. Do you think that's the appropriate around? So do you think it's the appropriate way to measure?
That is a real good question, because I have my personal view regarding the clamp test. Sorry, supervisor. Indeed, upon euglycemic conditions, people insulin resistant will for sure express their phenotype, require less glucose to be infused. If we want to expose these people to conditions where or similar to what they live during the 24 hours, most likely we need to expose them to hyperglycemic conditions.
And do you think it will, yeah, that's fine, thank you. But do you think it will make a difference if you have used hyperglycemia?
If I would use hyperglycemia?
Would you have seen different results?
I think if we use hyperglycemic conditions in these people, most likely next to the ability of the muscle to take up glucose, the mass effect might also take place. And the combination of these two events might influence for sure the glucose uptake in muscle.
So
and what happens inside.
So when I look at your data in figure 5, you have calculated some M values for the clamp, and I can see a variation in your data from perhaps a factor of 4, maybe more, even in the pre-training state. Do you think that is biological variation, or you think it's technical variation?
Indeed, it's something that we don't know. To avoid the technical variation, at least we try to standardize the precondition of this test by suggesting people to do not perform any intense exercise at least 48 hours before the test, to come over at a certain clock time and we repeat the same conditions in every single subject at the pre and the post-training. I think the variation of the clamp test is no higher than 10%, at least has been shown in different populations in terms of the glucose infusion rate, of course, in the same phenotype subjects. If this is something physiological, I would say that we need to go a little bit deeper and see what is going on with the tracer infusion and see whether the disposal of the glucose upon insulin effects might also express this variation or not. Because this, we need to keep in mind, is only the total infusion rate rather than the disposal. And that is corrected for body weight.
Yeah, so I agree, and but I also think it's a very big biological variation. In these, they are obese, but they are still healthy. And of course, this should remind all of us to be very careful when we look at data and trying to look at average, because we have this individual variation. You also have this in the response to your training. Some, as you said in your introduction, some are increased sensitivity, some are unchanged, some go down. So can we predict who is doing what?
If we predict, sorry?
Yes. So if you were in the gym and should supervise somebody to do exercise, then you would like to find out beforehand who would benefit and who would not. Can you predict this?
Yes, so as part of the discussion, I also indicated that the training status of the subjects might also dictate how well people will respond to the exercise intervention. So for example, the rate of change of the DU2 max correlates significantly with the rate of change of insulin sensitivity. So people who sustain physical activity in the regular basis might definitely respond with higher training adaptations, although it might also be controversial given the fact that we would expect to create a bigger room of improvement in people who are less trained. But according to the correlations that we executed, we might say that people who are more trained will respond better to the exercise-induced insulin sensitizing benefits.
So do you think you are recruiting the subject with the right parameters? Have you checked their leisure time, physical activity, or should that be a part of a selection process in future studies? Is that important?
For example, there are some other approaches where people predict the type of response or the magnitude of the response by using plasma value of certain metabolites, but that might require some expertise on more expensive tools. But also, for example, there are other easier ones that might only require to measure body fat composition, for example, on which people with more ectopic fat accumulation might require, or not might require, but might respond differently to people who have less ectopic fat accumulation, or simply total fat content in the body. That would be even easier.
Yeah. So I have just a last issue or question. So you investigate your subjects before and after a training session. And my question is, what is going on with, for instance, glycemic control after each individual exercise bout? So you compare this water versus carbohydrate protein diet. So do you think that on the daily, if you measure it on daily basis, do you think the intake of the carbohydrate protein diet have changed the glycemic control on the individual days?
Indeed, we would expect
Short answer, please.
We would expect that the consumption of glucose combined with protein might lead to a hyperglycemic peak combined with a hyperinsulinemic peak, in addition to the effect of the protein. If that influences the 24 hours post-exercise, it can be, nevertheless, the acute effect of the exercise might remain in muscle, as I say, and then blunt the hyperglycemic peaks that we might observe without exercise. So indeed, the muscle stays activated to take up the glucose coming from the drink, and therefore to maintain a proper glycemic value over the day.
Thank you, Mr. Candidate.
Okay, thank you. The opposition will be continued by Dr. Meeks, Associate Professor at the Department of Human Biology at this university.
Yes, thank you very much. Dear candidates, I would like to congratulate you as well with a very nice thesis, and also your promotion team, of course. It was really a pleasure to read your chapters, but obviously I do have some questions. And I would like to start with chapter 3 as well. I would like to go to table of page 50, and you report pre and post levels for both groups. And my question there is, why did you decide to use an unpaired t-test of the delta values? And would you not agree that a two-way ANOVA would be much more appropriate for this design?
Dear esteemed opponents, thank you very much for your question and also for the words. Indeed, applying a two-way ANOVA test might be more applicable if we are interested to see the effect of training. Nevertheless, as I stated since the beginning, we only wanted to see whether there are differences between AM and PM. Having two groups with a t-test is more than enough. If we would include the effect of training as a research question, definitely we would apply a two-way ANOVA. Okay,
but from what I understand, you are comparing post values versus pre values, and you want to know if your intervention in one group is actually give more pronounced results compared to the other group. So basically, I would say this is exactly the same design as you do have in chapter 6. And in chapter 6, you actually do use a two-way ANOVA. So you actually want to, what you're investigating, according to what I understand, is interaction. Is the effect in group B different from the effect that you see in group A? So would you still not agree that you have chosen the wrong statistical analysis?
I would say that the approach might not be the best in the fact that we included 3 different groups being trained in the morning or in the afternoon. But again, the delta value that we reported in both AM and PM groups reflect the effect of the training. As we wanted to only compare AM effects of exercise versus PM effect of exercise, the t-test is the more applicable and easier, not easier, but the most applicable method in this regard. Again, if we would be interested to see what is the effect of the training per se, and compare again AM versus PM, I would apply a two-way ANOVA. But I would stick to my plan of applying the t-test only by comparing delta values between AM and PM.
Okay, that's clear. Then I would like to go to chapter 6. You mentioned in the introduction that compliance to the regular or conventional training is quite low, and it's hard for individuals to stick to the training regime. And then on page 127, you actually state that HIIT training represents a time efficient alternative because it only costs 30 minutes of exercise a week. Now, I would find that a very misleading statement because there's also the time that they rest on the bike, and basically the time that they do exercise or are sitting on the bike is just as long as regular exercise. Would you not agree with that?
If we quantify the time that the people stay sitting on the bike, yes. But if we quantify the time that people move the legs, it's way lower. In that regard, we only have a training protocol where people exercise for 10 minutes and rest for 20, versus the other protocol where people who are sitting on the bike, for example, are exercising for 30 or 40 minutes.
Yeah, but in that regard, it's not time efficient because when they go exercising after work, they just lose as much time with the HIIT training compared to the regular training.
Indeed, I agree with that. But if we quantify the active time, we are using a protocol which is much more efficient as compared to the conventional training program.
Okay, so basically what you're trying to say is that the amount of time that they have to be active is less. And so it may be easier for them to do those kind of training sessions.
Definitely. Yes.
Yeah. So I'm always a bit surprised about the idea of using HIIT as a way to replace regular training. Many years ago, I did interval training myself and I dreaded those sessions. So why do you think it would be useful for type 2 diabetics?
Indeed, I think it's useful given the fact that we use short time windows to be active on the bike, in this case, only 1 minute. That is followed by 2 minutes of resting, on which we use still a high intensity, being between 80 to 90%. But if we go back to the literature where people use this type of exercise, where all-out exercise, where they use, for example, 200% of the maximal power output, that is double, even more than what we use at the moment. So I think it's pretty much a good training method to be applicable in type 2 diabetic people.
Thank you very much.
Rodrigo Fabian Mancilla Fuentes, the time appointed for defending your thesis has passed. The degree committee will now withdraw to discuss the quality of your thesis and your defense. And I request that you and your company await the results of our deliberation and our return to this room. Rodrigo, Fabian, Mancilla Fuentes, the degree committee here present has assessed the quality of your thesis and your defense. In view of its positive verdict and taken into account your previous qualifications, the degree committee has decided to grant you the degree of doctor. Professor Hesselink is authorized to confirm upon you this academic distinction in accordance with Dutch university custom. I invite your supervisor to now take the floor.
Do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent, and responsible?
Yes, I promise.
By the authority vested in us by law and in conformity of the decision of the committee here present, I hereby confer upon you, Rodrigo Fabian Mancilla Fuentes, the degree of doctor and grant you all the rights attached to this by custom and law. As evidence of this, I'm happy to present you with the degree certificate signed by the rector, the secretary, and the other members of the committee, and affixed with the official seal of the university.
Beautiful.
Dear Dr. Mancilla, dear Rodrigo, it is my pleasure to be the first to congratulate you with your newly obtained doctor's title. And my congratulations are also on behalf of Vera and Joris and the rest of the DMRG team who's in the audience. I'm really happy and proud to be part of this special moment. I also would like to congratulate your son Benfita and your wife Lorenza and your parents with this achievement. I trust your parents are on the online session, I hope. The festive moment that we have now is also a moment to look back a bit and see where you have come from. It must have been back in 2014 when I first met you. You started the master program Human Movement Sciences, for which you had to do an internship. I was approached by the internship coordinator with the question if we had room for an ambitious and dedicated Master in Science student from Chile. Honestly, we were somewhat reluctant at that stage. We were running quite a few projects. The internship period was relatively short. The projects we had were predominantly human intervention studies, in which verbal communication with the participants in their own language is key. And our participants typically originate from this region, so they do not really speak Spanish nor English. Already in our first discussions, you clearly turned out to be a very dedicated and determined student. Your enthusiasm and dedication made us decide to offer you the internship position, and you started doing analyses on NMR spectra that were obtained to measure diurnal variations in liver. You did a good job. You provided a nice overview of what you had been measuring, and as often is the case, after a successful completion of your master thesis, you finished your master, you left the group, and you went back to your home country, Chile. It was not long, however, before you contacted Patrick, asking if we were interested to support a project proposal from your side, submitted at the Chilean Committee of Investigations, CONICIT, which, if successful, should end up in a PhD position in the group. One might wonder what made you go all the way from Chile to Maastricht. I was wondering as well. So I approached your former mentor, Eric Diaz, to ask. And this is what he told me. Rodrigo, you are our hero. You came from the remote city of Coyhaique in the far south of Chile. You traveled some 1,000 kilometers north to Temuco city to become an excellent PE student. And then you decided to take the greatest challenge in your career, such as going to pursue a PhD. A PhD at Maastricht University, in the opinion of Eric Diaz, the best place worldwide to study exercise and human metabolism. And obviously, I won't debate that. So briefly, we discussed the possibilities and the research ideas you had, and you started writing the research proposal. And after a period of silence, it turned out that you actually won the grant, and you could start your PhD here in Maastricht. We warmly welcomed that news, and after some logistic hurdles, you returned to Maastricht in December 2016. And I must admit that prior to your arrival, I had not really looked into your private situation. Other than that, it would take you some 24 hours plus and some 3 stopovers to bring you from Temuco to Maastricht. And when you had arrived, we also had a project submitted at the effect of high-intensity interval training in obese individuals on metabolic health. Luckily, also that project got funded, and we hired Maaike Bergman, one of your paronyms, on that project, and the two of you teamed up together and jointly made this project, which is part of your thesis in chapter 6, made it a big success. And after a couple of months, you were asking for a few days off, as your wife and your son were coming over. And it was only then that I really started to realize how big a game changer it must have been for you to move from the gate of the Patagonia Mountains to the Limburg Hills. For me, this was the explanation for your dedication and your determination that you displayed throughout the project. I think you enjoyed doing the HIT project together with Maaike, but you also mentioned that you would like to run a dedicated project next to the joint project. And again, we were somewhat reluctant. Yes, I'm a stubborn supervisor, and you are a critical PhD student, which is very good. But you insisted, and the experiments in the mitochondrial inertia outlined in chapter 4 are the tangible results of your perseverance in this respect. I trust this chapter will turn into a nice publication, hopefully with support of our colleagues at Duke University in North Carolina. And then, all of a sudden, with the HIT project running smoothly, Corona came. Without being invited and without permission. But soon it became clear that Corona came here to stay. This was complicating matters for many of us. Complicated situations at home, remote school, Zoom meetings in the kitchen, forced application of the project, no fun at all. It's even bothering us this week. We had to work on a stand-in opponent yesterday. You had to work for a stand-in paronym the day before yesterday, and it was only this morning that I heard that it's very unfortunate that your parents could not make it today to come here. But okay, you've proven your resilience. You've taken those challenges as an opportunity to work on retrospective analysis of the data that there were on timing of exercise. And since then, we also know that we are better off training in the afternoon than during morning hours, at least when it comes to improving glucose homeostasis. So it is about time to stop this laudatio, to permit everybody to start doing his or her afternoon training session. But I would not do so without expressing my sincere gratitude to you, to Vera, and to yours for making my life easier when I was not in a position to contribute my share to the project for some period. It was no longer just Corona that was bothering us. So for me, this also is a very special day. Thank you all from the bottom of my heart. The final words are to your son, your wife, and your parents. To start with your parents. We are very thankful that you, as parents, were so brave to let Rodrigo discover the world and leave from the south of Chile all the way to the south of the Netherlands. You can truly be proud of Rodrigo, of his achievements, and I really do hope you're still in a position to come over and we'll have a good time together. In the words of Rodrigo's mentor, Eric Diaz, we, as Chilean scientists, are very proud of Rodrigo's achievement today. All the best, my dear friend. That's what he said yesterday. For Benrita and Lorenza, just a few words to let you know how much we have appreciated the hard work of your father and husband. Also in times of uncertainty and unclear future perspectives, you have been supporting him. It was a great pleasure and a relief to us when we heard, just before Christmas, that you managed to secure the EFSD grant, which puts you now in the position to work for 1 more year as a postdoctoral fellow here in Maastricht. We cannot predict the future, but thus far, Rodrigo, I think you have been proven to be able to bend the future into your own direction. I think you could not have done anything better than this. Thank you all, also on behalf of Vera and yours. Ik heb gezegd.
Thank you very much.
Dear Dr. Mancilla Fuentes, also on behalf of the Board of Deans, I congratulate you with the honor you have acquired. And we wish you all the best in the future in your research on nutrition, in the interaction between nutrition and exercise, as you have demonstrated in the last hour, and of course also in the promotion of metabolic health in humans. It's now a pleasure, in fact, for me to announce that after Hora Est, it's now time for Horeca Est, and I will invite the audience, in fact, for the reception. But before we will join you, we will make a picture here with the new doctor in front of the audience. And hereby I close this ceremony.